So Marco Salvi is a principal research scientist at NVIDIA, where he works on developing high-performance software and hardware rendering algorithms for the post-Moore's law era. His research interests span a broad range of topics, from anti-aliasing and order-independent transparency to ray tracing hardware, texture compression, and neural rendering. Marco has made numerous contributions to rendering APIs, including raster order views and micromeshes, and his early work on real-time neural image reconstruction has led to the development of NVIDIA DLSS. Prior to becoming a researcher, Marco worked at Ninja Theory and LucasArts, architecting advanced graphics engines, performing low-level optimizations, and developing new rendering techniques for games on 2 generations of PlayStation and Xbox consoles. Marco holds an MS in physics from the University of Bologna. I can't pronounce that. Bologna, Italy. Anyways, thank you very much for coming, Marco, and go right ahead.
Good morning, everyone, and thanks for coming to my presentation. As you just heard, my name is Marco, and most of my research typically ends up running in shaders or deep learning frameworks, but I occasionally pretend to be a hardware architect as well. And today I would like to talk about the impact of deep learning techniques on real-time rendering pipelines. Nearly 6 years ago, I gave a presentation at SIGGRAPH attempting to convey the idea that the new kid on the block, also known as deep learning at the time, was not a fad, and it was likely to have a profound impact on rendering. The presentation even included some of the early ideas that eventually led to the development of DLSS, but at the time I tried to not sound too confident, and I remember toning down my enthusiasm for the subject, given how uncertain everybody, me included, was about its future. But today I believe most of that uncertainty is gone. While we are still in the early, I would say very early days of this technology, neural methods are impacting not just the way we render images, but also the content that we create. And today I'd like to try to understand where we are right now and where we might be headed in the near future. And before we begin, a fun fact. The original title of this presentation was Blurring the Line Between Physics and Hallucination. But ChatGPT found it kind of dismissive and proposed to use imagination instead. And who am I to disobey our new AI masters? So here we are. So let's get started. These days we hear the word neural being used a lot in our field. But since not everybody is a practitioner, we first need to clarify what it really means. And the term is rooted in artificial neural networks trained with stochastic gradient descent. These networks are inspired by the brain, but don't really resemble their biological counterparts, which are far more complex. But over time, the meaning of the word neural has evolved to encompass pretty much any computer program that makes use of optimization methods, including and especially stochastic gradient descent. Of course, there's nothing special. Oh, sorry, I forgot to show you the network plus stochastic gradient descent and the programs plus stochastic gradient descent. And of course, there's nothing special nor neural about these programs. They don't necessarily even use any constructs that could be loosely associated to neural networks like multi-layer perceptrons. It is all just code combined with gradient descent all the way down. So if you don't know the word very well, don't be afraid of it. It's really, really simple. Now, one of the most striking developments in recent years is that the very combination of code and gradient descent joined with a culture of publicly releasing code and data sets has made it much easier for ideas to cross-pollinate fields. For instance, AI, computer vision, and rendering have to some degree started to blur at the edges, to blend at the edges. They become sort of co-travelers with loads of new results popping out on the internet every single day. It almost feels like everything is moving forward so fast, and it is hard to keep up, at least for me. And for this reason, in this talk, I'll use this mainly as an excuse to focus on the advancements that more directly impact what we call traditional rendering pipelines, which means ray tracing and rasterization these days. But of course, there is a lot more work, excellent work that I'm not going to talk about today. And so let me draw a very abstract representation of a real-time rendering pipeline, and I'll be doing this with taking a few creative liberties. We start with visibility determination. Whether we use ray tracing or rasterization, it doesn't really matter, but eventually our rays must hit, our rays hit must be shaded, and so we evaluate the material and how it interacts with light. When we do this, we often need the help of a texture sampler and also the help of a frame buffer to write out our intermediate or final results. And obviously, we might be doing this multiple times. Perhaps we have multiple rendering passes or multiple bounces in a path tracer. And finally, these days, it's quite likely that at the end of the pipeline, we will find TAA with or without some form of upsampling. Now, if we want to introduce neural methods from scratch, starting from the tail end of the pipeline is a less risky proposition. Since we can try out new ideas in a renderer agnostic fashion, and the rest of the pipeline basically can remain unchanged. And TAA is the perfect spot for experimenting with these new tools. And this is exactly what I did in an early test a few years back. I replaced the box filter that is typically used in TAA to generate the color space bounding box used to accept or reject samples from previous frames. With filter weights learned through gradient descent. So instead of basically replacing a box filter with something learned through gradient descent. And the results obtained were quite interesting. So this is a TAA, an image render with TAA in Unreal Engine 4, I think. And this is the same image render with this learned TAA. So the algorithm has not changed. We only fine-tune the weights using gradient descent. And as you can see, as I go back and forth, I hope you will be able to see on the big screen. There is a bit of latency. But I hope you will be able to see on the big screen or on the other screens that the learned TAA image looks quite sharper. And so it's not a dramatic difference, but it's definitely image quality has improved. So these first results were already quite exciting, but eventually we found out that we can do much better if we replace the handcrafted heuristics used to reject or rectify the color samples from previous frames with a convolutional neural network. And this is pretty much how DLSS was born. And let me show you another result from Unreal Engine 4. This is an image render at 1080p resolution with TAA. And this is the same frame rendered with DLSS, but a quarter resolution. So we are only using a quarter of the samples. We are rendering at 540p. Let me again go back and forth. And if you look at these, oops, I hope you can see the mouse pointer. Yes, if you look around this region here, where there is some text, as I go back and forth, oops, you should be able to see a fairly significant difference in sharpness. So much better than what we were able to obtain with the learned TAA. So this is a significant improvement. And as I mentioned earlier, DLSS doesn't impact the rendering pipeline in a major way, since it can be used more or less as a replacement for pre-existing temporal anti-aliasing and super resolution methods. So these impressive results obtained with it suggest we ought to be able to do more than just adding samples within the current frame. We should also be considering to generate whole new frames instead. But to predict next frames, convolutional neural networks must understand the motion of objects and how the motion affects the scene over time. Usually, CNNs struggle with this, as they tend to recognize textures and not the structure of objects, which is why these models are often spoon-fed with application-generated motion vectors. But if we try to use this motion information to predict the next frame, we often get incorrect results. For instance, in this case, the motion vectors from the application suggest that this shadow here cast by the bike is moving with the ground instead of being anchored to the bike, causing a sort of double vision effect. You can see that part of the shadow is still with the bike and part of it is sort of being blurred away by the fact that the network doesn't really understand motion properly in this case. And so this is yet another case where it's hard to engineer a simple analytical model to understand what should be done and do the right thing. So we should replace, again, a bunch of heuristics with a network. And this time, we're going to use these new tools that we have at our disposal to analyze both the motion vectors generated from the application, here, the one up here, you see the shadow is still incorrectly determined as being moving, together with the motion vector generated with a harder optical flow engine that is comes often with modern GPUs. And you can see that in this case, the optical flow engine determined that actually the shadow is not moving, because correctly so, because it's basically anchored to the bike. And now our CNN can predict a new set of improved motion vectors by sort of synthesizing a new motion field from the two inputs, allowing for a much better tracking of the motion of shadows, reflections, and other intricate details, which results in a far, far more accurate frame generation results. And now you can see that the shadow is in the correct place. Now, these are the main ideas behind the DLSS3, which can provide significant performance improvements over super resolution, especially when the CPU or the GPU are limited. And but the most exciting thing, at least to me, is that we are rendering in the traditional way only 1/8 of the pixels. With neural rendering already providing the remaining 7/8, and we can do this while leaving pretty much all of the rendering pipeline unchanged. And given that Moore's law is running out of steam, I believe that this form of data amplification is going to stay with us. I believe it's becoming increasingly clear that the job of the renderer is not to render images anymore. Its new job is to render samples, or at least enough of them that neural reconstruction can still build a compelling image at high frame rate. And the notion of what those samples are today and what they're going to be in the future, I also believe it is going to change. So to see how, let's go back to our rendering pipeline diagram. As you can see, we have replaced TEA with a neural image reconstruction, and we think it's not going away anytime soon. The natural next step is to recognize that all samples we feed reconstruction with are modeled after quantities that are intuitive to us, to human beings, quantities like color and normals and depth, things like that. But they're not, these quantities are not necessarily the best bang for the buck for the reconstruction algorithm that is not constrained by human likings. And since the neural methods can help with us learning new representation, it would be compelling to replace these old samples with new learned representations, and the frame buffer is the right place where to do this. Even more interesting would be to use these neural methods to attack basically an old standing problem of order-dependent transparency. Early in my career, I worked quite a bit on this topic, which is dear to me. And I hope that this talk might convince some of you that this is still a very important and not really satisfactorily solved problem, especially for real time. And it would be worth looking at it again with these new tools. And if we keep talking about parts of the pipeline that haven't seen much change in a long time, it's hard to ignore the texture sampler. How the compressed texture formats have not improved in a long time, and they still offer some moderate compression and only can handle only 4 channels at maximum. While in the meantime, texture resolution has kept going up, and also the number of channels in our material textures has kept increasing because most renderers have embraced physically based rendering. And so we are a bit of stuck in the past. So let's see what we can do about it. Let's take in consideration, for instance, a set of textures for a PBR material. Here I have 10 channels, and I'm visualizing all of the channels like if I were storing them in these 4 different textures, and also their MIP chain. Now, BC formats exploit data correlation over a small 4x4 tile, and typically they build a linear model over that small tile. And they also have a very small sort of a receptive field, both in the space of the texels and also in the number of channels, as I said, up to 4. And this is not really very optimal because intuitively speaking, if we just look at this texture, you can see there are a lot of repeating patterns across all of the channels. So there's a lot of correlation across the channels. So, and also a lot of correlation between the MIPs. The same patterns are repeating, although at different scales down the MIP chain. So it's quite intuitive for texture like this one to think that if we exploited the redundancies across all the channels and all the MIP levels, we should be able to significantly improve compression. And indeed, we can, and we did, as we detailed in our recent SIGGRAPH paper. we found that we can unlock 16 more texels using low bit rate compression with better image quality than AVF and JPEG XL. These are image compression methods that also use entropy coding and do not support random access, while we do. And let me give you an idea of how well we're doing. I hope you can see the pointer. Yes. Okay, so on the x-axis, we have bits per pixel per channel. And on the y-axis, we have PSNR. And our method is represented by this blue curve here. This is neural texture compression. And BC textures, we tested them on a data set of 20 textures over 2 different kind of presets for different quality trade-offs. And this BC is more or less around here. If we apply entropy coding to BC, we get something like this. But neural texture compression can provide far better quality and much lower bit rates. And you can see that it also at very low bit rates, it does better than AVF and JPEG XL. These 2 methods eventually take over when the bit rate increases, also thanks to entropy coding, which we cannot use if we want to keep having random access. And now let's see a bit more in detail how this works in practice. Since we want to retain the ability of performing random access, we store our compressed representation in low resolution grids, often with 16x or even 64x fewer texels than the original texture. And we store these low resolution grids with lots of channels, but highly quantized. Typically with 2 or 4 bits per channel. And when we need to decompress a texel, we fetch the needed latent code, and we feed it to a small decoding network, which is specialized for each material. So you can imagine that we're not just specializing the way we represent the texture with the latent code, but also specializing the decompressor, which is essentially stored in the weights of the MLP. And we pass this latent code to the decompressor, to the decoder, alongside LOD, because since this is a unified representation, we also want to tell the MLP which level of the MIP chain we want to decode. And also we pass a form of positional encoding. Typically, positional encoding is used in networks that represent a signal in their weights. This is not our case for a parametric network like ours, since most of the information is stored in the latent grid. But since our latent grid is a very low resolution, this tile positional encoding helps the network sort of upsample the information within one of these low resolution tiles that represent our latent code. And the output of the network of the decoder is the decoder texels we can use in our shaders. And to compress a texture, we use surprise, stochastic gradient descent, with backpropagation, which effectively runs the pipeline backwards from the decoded channels all the way back to the quantized low resolution grids, and in the style of autodecoders. Essentially, the decoder becomes an encoder at backpropagation time. And compression can be done very efficiently on a single CUDA kernel. We can write it by fusing both the forward and the backward passes, all in a single kernel, and trying to stay on chip as much as possible, and can take from a few seconds to a minute or 2, depending on the texture resolution and the desired quality level. And this technology could be used in different ways. For instance, it could be part of a streaming virtual texture system, in which case the compression could be easily done on entire pages, and it could be done on the GPU or even the CPU. But we wanted to prove to ourselves that it's possible to use neural texture directly in a material shader, and we were able to do so by inlining the network with the shader code and using registers to pass data to and from the tensor cores. We also overfit our representation at discrete texture locations. So we never train the network at arbitrary random UVs over the texture, but only at discrete texture locations, because it improves compression and quality. And basically, we're asking the network to not memorize all of the possible location over the texture, but just the discrete ones. But this implies that there is no guarantee of smooth reconstruction between the texels and the MIP and the MIP levels. Moreover, the network is non-linear, and we can't use hardware filtering to accelerate filtering. So we had fun implementing filtering in software, but it's very inefficient because essentially you need to invoke the network for each tap that you need to decode. And if you're doing something like an anisotropic filter, you might need up to 128 taps per pixel. So it would be incredibly inefficient to work that way. So instead, we use stochastic filtering, which relies on spatial and temporal neural reconstruction. So we come full circle now. We first introduced, neural temporal reconstruction, and now we are using it to also enhance and enable other neural methods. This way, we can just decode one important sampled tap per pixel, and we can usually support filters like Gaussian filters or bicubic filters that are not typically supported by hardware texture samplers. Let me show you a video that I capture on my machine. And so I don't know if it runs. It's supposed to run at 60 frames per second. I'm not sure why it's so choppy here, but it runs smooth on my machine. And as you can see, as you should be able to see, the result on the right is much more lower resolution because our neural texture compression neural texture has 16 more texels in more or less the same memory of the regular BC textures. And probably you won't be able to see this clearly from the screen, but when we magnify the neural texture, we also use stochastic filtering, so we get this nice Gaussianly filtered magnified texels. And now this idea of using the tensor cores directly inside shaders goes beyond decoding compressed data representations. And it was also used recently by some of my colleagues to accelerate real-time path tracing of photorealistic multi-layer materials. And this is the paper which was just released 1 or 2 days ago that details the results of their work. And the main idea behind this paper is to use a neural encoder to bake deeply layered material graphs into a compact, unified neural representation. There are several reasons for doing this. For instance, by mapping thousands of shaders to the same network, architecture, we can massively reduce the number of code paths and possibly diverging code paths on the GPU, which can easily translate to faster performance and improved and more predictable performance. Also, the neural models can serve as baked version of arbitrarily complex materials, making it potentially much easier to exchange materials between different workflows and tools. All we will need to do is to exchange in a fixed set of latent textures and a few kilobytes of network weights. But the aspect of this work that personally gets me the most excited, since I really like high performance computing, is that I'll show you in a minute, is that it allows you for a big step up in visuals without paying the full cost that we normally have to pay to render such many-layer materials in the traditional way. Now, the training process works over 3 phases. In the first phase, the model is trained end-to-end by forwarding the latent code here directly to the decoder by passing the latent textures entirely. After the decoder converges, we switch to fine-tuning phase. And in the second stage, the latent texture is initialized by evaluating the encoder for all texels, after which the encoder is dropped entirely. And basically, we have a last phase where the content of the latent textures are sort of also fine-tuned, trained directly with backpropagation through the decoder. And because the encoder only participates in training, but never at runtime when we need to render an image, it has no impact on the evaluation cost during rendering. And at rendering time, this is what happens inside the material shader. The neural representation, which is stored in this set of hierarchical latent textures, is sampled, and the resulting latent code is fed to 2 decoders. A first one evaluates the BRDF, and a second one performs important sampling. Both decoders include specific graphics priors that facilitate the work of the multi-layer perceptrons. For instance, the important sampling decoder here at the bottom predicts the parameters of an analytical 2 lobes BRDF rather than directly trying to predict the BRDF. This makes the work of the MLP much easier and is able to learn and predict much better results. Now, let me show you how this looks compared against the reference solution. To be clear, these renderings use thousands of samples per pixels, and they are not real time. And unfortunately, for some reason, the video is also choppy still. And this is another scene, and you should be able to see that it's a naked eye is pretty much to say it's impossible to see the difference between the reference solution and the neural material solution. And this is a short demo recorded live on a 4090. I'm afraid it will probably be choppy again here as well. But if you actually check the frame rate, it runs between 100 and 200 frames per second. So it's very, very fast. And we disabled the noises so that people could appreciate how fast it converges because it runs at such a high frame rates. It essentially becomes, almost final render quality in just a few seconds. And as I mentioned earlier, one of the most exciting aspects of this work is the performance improvement that we can get by replacing traditional material graphs with neural materials. These new representations achieve state-of-the-art rendering and state-of-the-art rendering performance, significantly outperforming GPU implementation, regular traditional materials implementations on the GPU. And often, it depends on the size of the network we are using, but the performance improvement can go from 2x to 9x on the scenes that we tested. And even more interestingly, for actually using in practical purposes, is that as we increase the number of materials that we have in the scene, and therefore the number of divergent data paths that we have, since each network, set of weights is trained for each independent material, the rendering time is not really affected that much. It scales very, very, very well, which bodes well for future use cases. And let me show you one last thing. It's not news that detailed materials can suffer from aliasing, as you can see here. We're rendered without supersampling, but this technique can render filtered materials without aliasing at any distance and without supersampling. You can see here in the image in the center that how the center image is how it closely matches the reference solution while just using one sample per pixel. And now I want to clarify that this is very early work, but we think it has the potential, as I mentioned earlier, to enable exploring materials from, enable exporting materials from and to any renderer, whether it's film or real time, using a representation that can be scalable and portable. For instance, here we had fun implementing these techniques in using WebGL. Of course, here there's no tensor core acceleration. All the MLP math is done in GLSL using regular FMAs, but it still runs pretty fast. Again, it runs at 60 frames per second in WebGL, but not on this screen. Now, simply relying on physically based light transport alone is not going to be enough to achieve photorealism in real time. Clearly, photorealistic content at scale is many orders of magnitude more complex that that artists can author today and fit in a game distribution and fit in memory at runtime. What we need are single representations that can go beyond the current limitations of geometry, textures, and materials across all levels of details. The works on neural texture and neural materials I just showed you are steps in the right direction, and I believe in the long run, the expressive, compressive, and generative power of these tools is what we need to make it practical to efficiently create, store, render, and manipulate in real time photorealistic scenes. I think that we have essentially two main roads ahead of us and to follow to achieve these sort of grand goals we set for ourselves. One of these roads, and I'm sure you saw this coming, is generative modeling. Text to 3D with diffusion models is a prime example of this. For instance, the fantastic Dream Fusion paper from Google and Berkeley showed remarkable results that have spurred a lot of activity in this area, and many, many other papers follow this first one. And the other main road, which holds a lot of promise and also is seen a lot of research activity, is inverse rendering, which is a very cool sounding name for the process of inferring the scene and object properties directly from images by reverse engineering essentially the image formation process. And for instance, I think nerves are a great example of this. Because, they're a good example how a problem can be simplified for inverse rendering. In this case, by building a rendering pipeline that is differentiable by construction, and then use backpropagation to learn the representation that fits it. But as Peter reminded us in his keynote, there is still a long way to go before nerves can become the primary 3D scene representation of choice for real-time rendering. I think one of the main limiting factors is that we are learning scene representation that are sort of entangled and prevent from easily teasing apart and directly controlling the individual degrees of freedom that we control with traditional scene representations. Personally, I think that we are going to worship at the altar of triangles for a little bit longer when we search for something better, assuming it actually exists. Also, triangle come with a lot of nice properties. A triangle is simple geometrical shape. It's easy to understand, store, manipulate, animate. And fortunately, inverse rendering can also be applied to traditional scene representation. We don't need to go completely exotic for this. And for instance, this work from NVIDIA Research and Alton University show how inverse rendering can be used to learn more optimal geometry and textures, improving both performance and image quality, which is usually something, it's not a thing in graphics that to be able to improve both usually. Let me just show you this as an appetizer, but this scene contains 5 billion triangles, and the left side on the image only uses 20 million triangles with models and texture obtained using this technique. And here the starting point is a fully differentiable rasterization pipeline, which is based on this pretty amazing previous work here on the right from Line et al. That builds a differentiable rasterizer on top of graphics hardware, and it can be embedded directly in PyTorch or TensorFlow and provides super fast forward and backward passes. The only signal driving the optimization process is given by the differences between the rendered images and the reference images, which act as a supervising signal. This image space error is backpropagated from the output all the way to the later presentation, which in this case is not a collection of vectors that are imperscrutable to human beings, but actually are real geometry and real texture, things that we can understand if not touch. This methodology allows to jointly optimize all of the aspects of the latent representation, with gradient descent automatically negotiating whether a detail should be going into the geometry or, for example, into the normal maps. And this sort of leads to a natural divisional labor between geometry and textures. And typically, the geometry might smooth locally to transfer detail to the normal map or the other way around. And let me show you a real-time capture how this works. Some initial geometry must be provided to the algorithm, and the closer it is to the target, the better the results that we get. And this is what's captured live. And in this case, the mesh on the right was simplified with traditional level of detail algorithms for geometry. And as you can see, the inverse rendering is rapidly learning to adjust the geometry and learning the textures mapped on the geometry. And it does this directly from appearance. And you can see the final results. This is a breakdown of the later representation. And so this is the learned geometry and the normals. And other material properties. And of course, we went from a 300K triangle model to only 7K triangles. We can also learn pre-filtered material properties directly from reference high-quality images. Here, the model on the left, which is rendered with traditional MIP chain, is displaying a lot of aliasing and flickering. when minified, while the center model only displays aliasing on the edges because we are only using one SPP, but essentially has learned to generate a MIP chain that gives you the desired appearance from the reference solution with just one sound per pixel. Now, the previous work requires a starting mesh proposal, and this follow-up work done by Video Research in collaboration with the University of Toronto and the Vector Institute does away with that entirely. Here, the idea is to leverage some of the previous work, on deep marching tetrahedra, which is a hybrid 3D representation that can describe a shape with neural STFs, which are defined over the vertices of a deformable tetrahedral grid. So the STF can be converted into a triangular mesh using differentiable marching tetrahedra, which is an old algorithm, or a part of the differentiable part. And the loss, which is computed as usual from the renderings, provides the supervising signal that is propagated to the implicit field and allows to basically update the topology of the mesh as the training process goes along. And this allows basically to jointly optimize not just the surface, but also the render that appears end to end. Let me show you how this looks in practice. This is also a capture, but this has been accelerated a little bit. But you can see, actually, let me restart it. You should be able to see how initially on the right, there is a sort of cloud of triangles, comes from the tetrahedral grid. Oopsie. Okay, great. Doesn't want to play it anymore. Okay, I'm sorry, I'll let you skip this. Okay, sorry, the video is not working anymore. Hopefully the next one will work. And so a bit like nerves, these algorithms can also be trained from 2D pictures, from photographs. And this is the very constructed model, as you can see, which, unlike with nerves, is not an entangled representation. So we have all the degrees of freedom of the scene representation that are available to be manipulated. So we can change the material. We can even use the geometry for a cloth simulation, and we can change the lighting environment and so forth, like we would do with a traditional render, because essentially it's being rendered using a traditional render now. And now I want to clarify that this is still early work, and a lot of more needs to be done before these methods can be fully embraced in production. On the other hand, I believe this whole endeavor is very promising, especially if you notice how much progress was done in the last 2 to 3 years, when all of these techniques really didn't even exist and were even thinkable. And I'd like to leave you with some parting thoughts. So far, we have either explicitly or implicitly used methods that to some degree are grounded in the physics of light transport. Yes, we make tons of approximations, but even when photorealism is not an objective of a particular application, we still rely on physically plausible processes to render our images. This is still true even when we use learned neural representation, for example, nerves, as they borrow essentially priors from volume rendering, which is also have light transport as foundation. But if we look at diffusion models, they do not make any use of physically plausible processes for image formation. As far as I can tell, there is no notion of light transport in these models, which progressively transforms samples drawn from a known distribution into samples drawn from a desired distribution. Nonetheless, they still generate wonderfully photorealistic images like this one, which last night took me about 5 minutes to generate, and is absolutely amazing. The geometry and the lighting are so rich with exquisite detail that thinking how we could create this, both the content and render this with the traditional render, almost hurts, because it would be very, very, very hard. And not long ago, I was thinking about this, and I happened to stumble on this on this Twitter post by Martin Nebelong, someone who I follow because he has mad modeling skills. And he took one of his simple creation on the top here and used the runaway Gen 1 diffusion model condition on the image on the top to create this short video, which made me feel both scared and excited at the same time. Yes, temporal stability is not great. Sometimes the salad becomes a fry and vice versa. And in some cases, the beer is changing color or the amount of beer in the glass sort of changes over time. But if you look, for example, the subsurface scattering on the fries is crazy good. And so I'd like to conclude my talk asking a simple question, to which personally I have no answer. Maybe you do have an answer. I'd like to hear it later. So what if we were wrong all along, and there is a much better way to generate photorealistic pictures in real time that makes both content creation and rendering easier and inexpensive, and then looks nothing like the renders we have dreamed about for decades now, because it's not grounded in the physics of light transport. And with these sobering thoughts, I want to thank you for your attention. And I also want to thank the many, many people that have inspired or contributed to this talk. I'm here just to represent really their amazing work. And also this list is far from complete. Sorry if I left you out. Yeah, thank you for listening. And
thank you, Marco, for amazing and inspiring and a little bit scary talk. So we have time for some questions. So please raise your hand.
Hi, thank you for the talk. So about the neural textures, you showed us an example where you compared one of the neural textures with the block compression. And in the example, they had both about the same amount of memory.
yes.
However, the neural texture took like about twice as long to decode, if I understand this correctly from the time.
Yeah, let me go back to the slide. It's here. What is it? Here we go. So let me.
So I would be interested if you also have an equal time comparison where the neural texture just takes a bit like less memory, but the decoding time is about equal. No, excellent question.
No, we don't have such comparison. The truth to be told, this is still research work. Is not hyper optimized, so this sort of performance gap that you see here is likely to get smaller in the future. We are, for example, we are not currently, as we detail in the paper, we use half precision math for the tensor cores. But since our representation is actually quantized only 2 or 4 bits, there is some hope we can make it work, for example, with 8-bit math, so which goes double speed on the tensor core. So there is hope to close that gap. Also, it might not be automatically easy to scale down the quality or improve the performance, or scale down the compression and improve the performance. The network we are using is very, very small. It's literally 20 kilobytes of weight. So there is a lot of room for scaling down there and getting much, much faster.
Okay, thank you.
You're welcome.
Hi, Marco.
Hi, Angelo.
Thanks for the presentation. It's very inspiring, really amazing. It made me think like we came a long way from, I don't know if you know, like the kill zone kind of half resolution interpolation that back in the days like created.
Yeah. I don't remember the details.
So reconstruction is definitely here to stay, and as you're saying, like it makes a lot of sense for it to climb up into further and further into the pipeline. Right?
Yes.
Do you feel that for that to be very, very successful, because right now you're saying like we're taking colors, normals, which are human quantities, that's true, but that they are also like convenient in a way where you can just plug it in the end. You have like a minimal intrusion. Maybe in the future you want even to change, I don't know, the way that you do raster and whatever to just feed into those neural concepts. But in that future, do you think that it needs to be unlocked by having this much more kind of in the open, like as standards, as things that everybody can, because if you like change the entire pipeline at that point, right, then it is very intrusive and you can't target it for a single vendor or things like that, right?
Yes, no, I see your concern. The answer is I haven't thought a lot about this, so I really don't know. Certainly, it's a valid concern, but I don't have a strong opinion either way today. Also, I'd like to add that you still have to be proven that changing the representation, for example, changing what we saw in the frame buffer and making less human-centric is actually going to improve things. My comment was more about trying to inspire people to try something different and see what works and what sticks. But it does work for textures. So.
Thank you for the amazing talk. It seems that in all the approaches that you've presented, it's always data-driven, all the neural approaches. And in the end, it's kind of overkill because it's always like we feed the data distribution that we're given with. So if I have a low resolution input, then I can use the best model I have. It's never going to be able to reconstruct something that is finer. And we're not like, but we know that, for example, given developers, they have the capacity to generate content somewhere, somehow differently, for example, with procedural rules that embed more inductive priors and rules to get finer resolutions or the diversity from a very compact representation. And do you see that, do you think there is something to be done here?
Yeah.
And if yes, how?
I think Bart is a big proponent of this. Well, we have something, actually, some comments about this, I think, in our textbook paper in the conclusions. For example, you can imagine how in the future you might have a network that not just decodes the texture, but as you magnify, might actually sort of hallucinate new details. I don't know if that answers your question or goes in the procedural direction you were thinking about.
Yeah, my point was probably more about like, because if we look at all the methods we have so far, it's always like we plug in an NLP and we're
Yes.
gonna try to find a good input to add it but we're not building on more complex architecture that might embed the rules themselves. You know,
Yes.
You model clouds or you model like wood or something like this. L systems of these things are infallible. And,
yes.
And for now, I don't see anyone kind of doing that for rendering. And I'm curious.
Yeah, no, that's excellent comment. I don't know much about L systems. I wonder how differentiable they are. So they might be hard to maybe optimize using gradient descent. But I remember seeing a few years ago some wonderful work about with neural cellular automata that produced some remarkable results. I never played with it in practice, so I don't know if they have a future or what the problems are. I haven't seen much follow-up work on those amazing initial results, so maybe there was some body buried in the ground that made them not so exciting as they initially thought. I thought they were.
More question? We still have 2 minutes.
Great talk, Marco.
Thanks, you're hypey.
So one of these denoised images that we have now.
Sorry, I cannot hear you.
One of those denoised images that you showed that's path traced, the rays that go into it, there's a spam of them from my eye.
Oh yeah, yes,
and
yes.
then they bounce all over the scene, and then they
Yes.
create textures which are themselves fairly compressed. And if you just got rid of that ray organization, that spam rays all over the scene,
Mm-hmm.
and then query textures and maybe some sort of scattered rays here and there. Would it be surprising if it's like an art store of rays or like blue set rays?
So I couldn't listen. I couldn't hear very
Wouldn't
well.
it be surprising if the rays that we have historically taken to do a path tracer are the ones you want to feed a neural network and some completely different type of set of rays?
Yes, I don't know, but it's an interesting thought. But it's, from looking at this image, by the way, I generated this, the prompt is graphics researcher worshipping at the altar of the triangle god. So, it has some amazing lighting that, again, I'm sure that if we were trying to build the same model try to reproduce the lighting, we wouldn't get it this way because it probably is wrong. And so this suggests that these models are learning maybe some concept of light transport, and maybe in the future might be fed in the way you just said with rays and might learn how to do the rest essentially. But I think it's too early to.
Can I ask? Thank you. This work on texture compression is fantastic. I was just curious if you have, I've saved the paper for the air flight home, but have you looked anything into 3D textures, or why not 4 or 5D textures? Or yeah, do you have any results on that?
There is a paper already out from NVIDIA, maybe no research, but from NVIDIA about neural VDB, which is, I think is a talk paper. And they use a different approach from what we used. They actually store the compressed representation for the volumes inside the network weights, instead of having a parametric grid like we do. I think the approach that we used could be extended to volumes. Of course, more work needs to be done in the area, but it seems it should be directly extendable to 3, 4, any number of dimensions really. It's just a grid. Whether, of course, it could, maybe other problems we are not aware of. But maybe you want to read the neural VDB paper is already been out for a few months.
I'll do that. Thank you. Fantastic work.
Thank you.
Any more questions? If no, let's thank the speaker again.
Thank you.